Okay, we're looking at work, energy and power for Year 12 Mechanics. So let's start with work. Work is defined as force times distance. And that equals work. Now that also will equal to a mass, which in this case would be kilograms, times an acceleration, which would be meters per second squared, and then of course multiplied by distance. Now that'll cross out, which will give us a unit of kilograms meters per second, which equals a joule, unit of energy. So 1 joule equals 1 kilogram meter per second. So that's our basic unit of work, and if we were to plot a graph, which would be a force and displacement graph, so Newton's up here on the y-axis, on displacement on the x-axis, apply a force constantly over a certain distance. The area in that graph would be force times distance and equal to the work done. That just gives a bit of a graphical representation of what work is. Okay, now let's look at an energy. What is energy? Well, energy is a capacity to do work. Again, its unit of measure is a joule, which we've discussed before. And there's several different types of energy, lots of different sorts. We're going to be concerned chiefly with mechanical energy. I mean, there's electrical, there's heat energy, there's lots of different sorts of energy. And of the mechanical energies that we're going to look at, we're going to look at two primarily. One will be kinetic energy, and the second, potential energy. So kinetic energy is defined as mass times the square of the velocity divided by 2. So if we were to work out the SI units for that, we're going to have kilograms multiplied by the velocity squared, which would be meters per second squared divided by 2. And the potential energy, and kinetic energy, by the way, is energy due to that an object possesses due to its motion. So it's energy possessed by an object due to its motion. In contrast, potential energy is defined as a mass multiplied by acceleration due to gravity multiplied by the height of the object above ground level. Now, potential energy again has similar units, or similar kind of units. It is energy that an object possesses due to its position. Now, the energy that I've given you here is called gravitational potential energy, because it uses purely the body's mass under a gravitational field to provide the force necessary. So it's still force times distance. There's the force and there's the distance. But there is another kind of energy which we'll look at, a potential energy, which is called strain energy. It's a form of potential energy, and sometimes it's called just SE, strain energy, and it equals force times the extension, and usually it's applied to springs, so hence you get extension, but it could be in terms of bending. If you had a bow and you bent a bow, or really deformation, divided by 2. And sometimes that's shortened down to a half of a constant called k multiplied by the square of the extension. Now k is the slope of the stress-strain graph. Remember that stress-strain graph we looked at earlier? Some other parts of our mechanics where we dealt with strain, and we saw that there was all materials, metals particularly, had a stress and a strain, and that distance or the gradient of that part of the graph that displayed its up to the elastic limit, that gradient was called Young's modulus. Well, this constant is related to that, multiplied by the square of the extension involved. So that's strain energy. Excuse me for a sec. Okay, so we're back to talking about that strain energy, and basically related to springs, or most often related to springs in regards to engineering, but not always. Now, probably it's good for us at this time here to talk about something else, which is the law of the conservation of energy. And you may recall this, that the law of conservation of energy states that energy is neither created nor destroyed, but simply changes form. The law of conservation of energy. It's neither created nor destroyed, it just simply changes form. And what that means for us is that in regards to potential energy, we can say that the loss of kinetic energy will equal to a gain in potential energy. Or another way of phrasing that is kinetic energy minus potential energy equals 0. Yep. Alright, so you have an object and it's losing its kinetic energy. If its energy is to be preserved, it most likely will be gaining potential energy. So for example, imagine a ball being thrown up into the air. It starts off very quickly, then slows down as it reaches height and point of its, or apogee, the point of its top of its arc of its flight, then starts to return quickly. So it gains its maximal potential energy over here at the apex of its arc, and its maximum kinetic energy down at the base. But its overall energy remains the same. Now, important for you guys also to know about power. Power is simply the time rate of doing work. So it's a rate at which one does work. Now that's defined as work over time, and that can also mean work we know is force times distance over time, and distance over time is velocity, so it can also look like force times velocity. So power can equal force times velocity, and if it's units will be joules, which are the unit of work, divided by time, or joules per second. That will be the unit of power. Now, James Watt, who did most of the work on power, has given his name to this unit. So 1 joule per second equals 1 watt of power. The ancient measure was 1 horsepower, and that equals approximately 745.7 watts. So So there's a conversion rate. So often horsepower was mentioned, especially in regard to vehicles. You can easily see why that would be the case. And lastly, but not leastly, the concept of efficiency. Okay, efficiency is given the Greek letter eta, that form there, and it equals, well, it equals the power output of a device divided by the power input. So you can see that in most cases, that the power output will be less than the power input. And were it to be the same, you would have 100% efficiency, or 1-on-1. But in most cases, energy is lost due to heat, and particularly to friction. And that's why efficiencies are rarely 100%. Okay, so that's enough for work, efficiency and power in terms of definition. You understand a little bit about them. Okay, so we've looked at efficiency and law of conservation, energy and power. Let's look at a little question that might tie in a bit of this stuff together. So we've got here a car with a mass of 0.9 tons. It's travelling at a constant velocity of 80 kilometres an hour down an incline of 1 in 30. Firstly, calculate the power delivered by the engine if the value of mu is 0.4. Remember, mu is the coefficient of friction, so it can be static or it can be dynamic, whichever one suits. And 2, what power will be required if the engine if the car were travelling up the incline at 80 kilometres per hour. Alright, so here's the question, simple kind of calculation question that we should be able to sort of work through and organise ourselves. Let's start off with what we know. Power equals work per unit time, which equals force times velocity. So the force times velocity is probably the very useful one here now, because we've been given a velocity and we've been given, we can work out forces. Now, first thing to note is that we've been given an incline. So let's draw a free body diagram. We've got a long, narrow incline like that. We have our vehicle here, our car, and it's going to have a normal reaction force up here due to it's going to have a weight force down here. We're told that that weight force is going to be 0.9 tons, so that will make it 9 kilonewtons acting downwards. Now we're going to need to split up that weight force into 2 smaller forces. I'll explain why just now. I might try and grab another pen to show you. So one force will act along the plane, the other force will act at right angles to the plane. I'll explain why that's useful in a minute. Now if it's going down the plane, there will be a friction reaction force which will act opposite direction of the motion, which we'll call Fr. Normal force there called N. And we know this is a slope. We can work it out because a slope of 1 in 30 means that we'll have a triangle like this with 30 going up the ramp and only 1 rise. So using basic trigonometry, we can work out that this angle inside here is 1.9 degrees. And you can use that pretty simply just by using the sine. Pardon me. Okay. So the inverse sine of 1 divided by 30 will produce 1.9 degrees for us for that angle. Now let's do some calculations over here. These 2 forces over here, this vertical one, if this is 1.9 degrees, then this will also be 1.9 degrees. This little angle in here will be 1.9 degrees. This force flowing down here, let's call it force vertical. That's going to equal to it's going to equal to 9 kilonewtons cos of 1.9 degrees, and the horizontal force is going to be equal to 9 kilonewtons sine of 1.9 degrees, just from trigonometry, basic trigonometry. We can calculate those out. That one there, 1.9, 9 kilonewtons sine of 1.9 is 0.3 kilonewtons, and this one over here is going to equal to 8.99 kilonewtons. I'm going to work in kilonewtons, so they're significant. So we've worked out what the forces are along the plane and at normal to the plane. That helps us because we're going to resolve forces using equilibrium horizontally and vertically. So that's why we split up this weight force into horizontal and vertical components relative to the inclined plane. Now we're also told something else. We're told that we've got a limiting friction factor. So limiting friction is going to equal to FR. That's FR over here. And that's going to equal to coefficient of friction by the normal force, multiplied by the normal force, which according to our information here is 0.4. We've been given that in the question. There it is there. Multiplied by the component, which is the normal component, will be equal and opposite to the component of the weight force, which is perpendicular to the plane. So it's going to equal to 8.99 kilonewtons. And that will give us a result of 3.59 kilonewtons as our limiting friction. So that's also significant. There. Now, were we to take, seeing as this is an equilibrium situation, why is it equilibrium? Well, because this is moving with constant velocity. Now remember, an object remains at rest or removes with constant velocity unless acted on by a resultant force. So, moving at constant velocity means in equilibrium. So we can use our equilibrium equations. So some of the forces which are horizontal along the plane will mean, let's go this way, positive, will be equal to 0. Now that translates down to the fact that, let's look at the forces that we have here. We've got FR, now this way is positive, so FR, the frictional resistance force. One more thing I forgot to add onto this diagram, just looking at it here now and realizing, we also have a motor. So we've got a weight force down the plane, we've got a resistant frictional force, but we also have a motor pushing down here. And let's call that FD, for driving force, FD. So there's another force acting here now. We've got a component from the weight, the driving force, frictional resistant force. So FR plus this component of force here, which is 0.3 kilonewtons, minus FD, because FD is going in the opposite direction of our convention, all equals 0. That means that FD, put the therefore signs, is going to equal to FR plus 0.3 kilonewtons. Is that right? Not quite. So FR, or if I should say FR, yes, here's our mistake. FR moves up along this plane, the other two moving the opposite direction. So it's minus, this is a minus over here, minus, minus. So FR minus, here, two mistakes make one, don't they? FD is what we want, bring it across this side, we're going to get FR minus 0.3 kilonewtons is going to equal to Fd. Now we know what Fr is. Fr, we've calculated it over here. So that's going to equal to 3.59 kilonewtons minus 0.3 kilonewtons. Yeah? Which of course you can work it out, it all results into 3.29 kilonewtons. So that's the driving force pushing down the plane. Now remember, we're looking for the power. Calculate the power up here. So power is force times velocity. We now know the force, we know the velocity, so the answer to section 1 will be the power down the hill is going to equal to force times velocity, which equals to, this is the force, 3.29 kilonewtons. Now what we should do, well, we'll convert this to newtons in a minute because we want to get watts poking out of here. I guess we'll keep this and we'll do kilowatts. 3.29 kilonewtons. Now we've got to multiply by 80 kilometers an hour. Now this is how I do it. So it's 80 kilometers per hour. We multiply this by 1,000 meters per kilometer, putting the kilometers in bottom so they'll cancel out. Multiply it again by 1 hour over per 3,600 seconds. Then we'll get our correct calculation because kilometers will cancel out, hours will cancel out, and the remaining units will be meters per second, which is what we want for velocity. When you work all that out and calculate it all out, it comes out to 7.31 kilowatts. So that is the power required by the car to travel down the hill at 80 kilometers an hour constant velocity with that frictional resistance that we've been told is inbuilt into its system. Okay, so part 2, what power would be required of the engine if the car were travelling up the incline? So up the incline at 80 kilometers an hour. Alright, so for part 2 down here, we've got a slightly different diagram. So there's our angle slope, there's our vehicle. This time the force, driving force, Fd, is going to be up the inclined plane. Still got our normal force here. We've still got our weight force, which hasn't changed, and it's 2 components. And this time though, the frictional force, instead of pushing up the hill, it opposes motion and it goes down the hill. So there's the frictional force now. So there's our forces involved. Now, the power required to push it up the hill is going to be Fd, this time, going upwards, multiplied by the velocity. Now, we know the velocity is 80 kilometers per hour, that much is easy. So let's look at it. We go to sum of the forces horizontal, because the constant velocity means it's still in equilibrium. Sum of the forces horizontal go this way positive is going to equal to 0. So that translates down to force going upwards minus the frictional, because it's going in the opposite direction, minus this weight component of the force, which we already know from, we've calculated it up here, it's 0.3 kilonewtons, equals 0. Because, yeah, it makes sense. Therefore we can say that Fd going up the hill is going to equal to the sum of these two, which is 3.59 kilonewtons. We've already worked out frictional force up here, remember? There it is there. 3.59 kilonewtons plus 0.3 kilonewtons equals 0. So we can say Fd upwards is going to equal to 3.89 kilonewtons. Now we know the force. To work out power we need to be able to know the velocity, so it's the same calculation that we've done just above here. So we can work all that out. The power up is going to equal to, let's do it in newtons this time, 3,890 newtons multiplied by 800 meters, or 800 divided by 36 meters per second, and that calculates out to 86.4 kilowatts, or 86,400 watts. And there's our answer for up the hill. Okay.